I'm John Leidel. I'm a PhD student and a researcher at Texas Tech University in the Data Intensive Computing Lab. And this is actually a purpose-built RISC-V extension for data-intensive style computing. So a little bit about GoblinCore, aka GC64. The name actually comes from the old Seymour Cray quote on 1,000 chickens, but we actually thought goblins were much more menacing than chickens. So having a chicken core is not really all that interesting to us. So the overall goal of the project is actually to build a purpose-built programmable data-intensive computing architecture so we can run things such as sparse matrix vector, sparse data structures, graph computations, network theory style applications, and actually have a chance of building optimizing compilers, optimizing runtimes on these very, very, very simple RISC style cores. And no surprise there, some of the driving characteristics behind our architectural concerns are non-unit stride memory accesses. So we need things like scatters and gathers, and very, very, very memory intensive. So these tend to be non-deterministic or pseudo-non-deterministic, and they tend to be rather cache unfriendly. So with respect to architectural goals, we wanted a really, really simple ISA, hence our adoption of RISC-V. All of the low-level hardware support for what we call mutable concurrency, aka the relationship between tasks, threads, however you want to call the software construct of parallelism, lives in hardware. That means hardware actually handles all the task concurrency and task scheduling. And of course, we wanted to provide very, very well-defined mechanisms for how and when context switch events occur between these tasks. More specifically, we wanted to make it rather deterministic how and when tasks shared access to the core hardware architectural mechanisms. Unlike the sort of standard notion of the architectural definition of a RISC-V core, where you have a single register file associated with a single sort of ALU or core, we oversubscribe many, many register files or sets of register files associated with a single core, and we map in what we call a GC64 thread control unit. And what this essentially is it's a very small, what will likely be an RV64C unit that is microcoded to perform the thread context switching and thread context management mechanisms for each of the tasks. We build multiple of these into what look very similar to the concept of RISC-V tiles with a MMU and a request coalescing unit. And the reason why we put a memory request coalescing unit in here is because we don't use standard DRAM. We're actually coupling directly to hybrid memory cube style memory units, which have not just 16 byte, but all the way up to 128 byte memory request payloads, in which case we do more memory request coalescing to build up much, much larger memory requests. So into the actual architectural state that we define as a part of our RISC-V extension, we put in a set of user visible registers that represent things such as where is my task memory footprint live for things like context save restore, for doing my own register management, things like that. There's an additional register for my thread ID. It turns out if you write things like OpenMP, you do a lot of indexing of arrays by your thread ID, so you can make very, very efficient use of your own thread ID for the purposes of memory addressing. We have the locations of what we call the task queues and task exception queues. This is actually the hardware's notion of where to go get tasks and threads from. And we have a set of basic architecture description registers. We've actually put in one additional supervisor registers that we call G-key. This is an ongoing piece of research that we're doing that has to be modified based upon the current draft supervisor specification. And one of the idiosyncrasies with having hardware-driven task fetching and task management is a software thread can enforce or instantiate a new task or new thread that falls on a piece of hardware that it shouldn't have access to. So we're trying to build in inherent hardware mechanisms in order to prevent you from taking over the entire machine with millions and millions of little threads and thus collapsing any other possible work that can be done by other users. We also have a single arithmetic machine state register called G-count. What this actually keeps track of is the pressure by which an individual task puts on the core at any given time. And what we're doing is enforcing context switch mechanisms based upon that task's pressure. And the pressure of each task and each instruction by each task is actually mapped directly to what the compiler's notion of instruction scheduling is. So the compiler actually has inherent knowledge of how the hardware will schedule the concurrent tasks on the system. So from an extension point of view, our extension is based upon the RV64i. We also pull in the M and A extensions, so this is essentially a G-style RISC-V instruction set. We have optional support for floating point in both single and double precision, although it's not absolutely required. We have support in our sort of fork of the context save restore mechanisms. And we also have support for the extended addressing modes. And as Kirsty noted earlier, this is actually really, really interesting to us because in typical scalable runtime models like MPI, we really, really want to simplify those in order to use base addressing in order to get to any piece of the memory in the system. We actually have a low-level physical memory specification based upon the 128-bit addressing mode in RISC-V. So all of our instruction extensions are actually built on the R type. We do not add any additional formats and whatnot based on top of the base set of formats. And we group these into a set of integer, single precision, double precision load stores. These are basically scatters and gathers in all the different formats that RISC-V supports. The extended addressing instructions will actually support scatters and gathers on 128-bit addresses. Then the really interesting ones are the concurrency, the task control, and the environment instructions. So no surprise, if you've ever done typical scatter and gather processing on any vector architecture or the scalar architectures that support this, we do the same thing here. So it's very, very simple index loads and stores. The concurrency instructions, however, are very, very different. So the first one that's rather interesting is what we call the iWait instruction. So the iWait instruction actually plugs the thread control unit directly into the inherent hazarding model of that task's register file. And what it does is it essentially will pend the execution of any additional instructions for that task until you either hit a numerical threshold that comes in as an immediate value for that given instruction, or the hazard is cleared on the target register index that you're interested in. So for example, you can do what you believe to be a distant load operation or distant store operation that uses a very specific register. And that load or store may go all the way across some sort of on-chip network or all the way across some sort of system interconnect network. And you want to absolutely ensure that you don't begin executing any arithmetic work until that instruction is retired and the hazard is actually cleared. Well, now you can actually do that with an iWait instruction and schedule that in terms of the remainder of the concurrent threads, because if you actually exceed that threshold, what it enforces in terms of thread control is a context switch to a different task. The other one that we have is a context switch instruction itself, and what that essentially does is it forces a task to context switch regardless of what its state is. So if you know that you're waiting on a memory mapped I/O operation or some sort of other DMA operation or a very, very distant NUMA-like load or store, you can actually force that context switch to occur and wait for those memory operations to return. Task control instructions. These are rather interesting for those of you who like to write runtimes, because we've taken the basic operations that you need to write a low-level concurrent thread runtime system, such as pthreads, or we actually have worked on building this as an OpenMP backend for RISC-V, and built those into a series of microcoded instructions in the ISA. So you can spawn tasks, you can join tasks, You can actually ask the system, where do I get new tasks from? And the reason why we have this here is in order to support things like work stealing. So I've completely exhausted all of the work that I know about. I need to go over to some other processor and find its concurrent work and begin fetching as well. You can get your thread ID. Then you can begin modifying what we call the task queue values. And these values actually represent how you distribute work across the system. And all of these task queue and task concurrency instructions play into the following task layout. In addition to the base ABI and the base RISC-V extension that we've defined, we're actually also defining the data structures that hold and maintain the notion of tasks and threads in the system. And we have to do this in order to allow the hardware to have a chance, or even the microcoded hardware to have a chance to successfully fetch all the necessary bits from where it believes those bits actually live in memory. So as a part of the low-level runtime kernels and the low-level runtime libraries, we actually enforce this queuing structure inside the hardware. And providing that you actually behave and adhere to the following structure, then the hardware will do all of the necessary joining and fetching of all of the thread state or task state that you need to. And we actually have a much further definition of this within our RISC-V extension document. So in terms of future development, our core architectural specification based upon RISC-V is documented. You can grab it. Following this meeting, I was actually going to post a note to the RISC-V mailing list and accept comments and questions and whatnot, and see if anyone else is interested in using some of the definitions we've used. What we're actually working on currently is based upon the notion of sort of the low-risk style minion cores. We're taking and developing some very small RISC-V, and we're debating whether or not to move over to the compressed format, but we're actually building microcoded memory coalescing units. So you have many, many tasks and many, many processors pushing memory requests into the MMU, and rather than servicing those with cached operations, we take those and we use a tree-based structure to coalesce those into the largest possible hybrid memory cube memory request payloads we possibly can. So you can think of having a bunch of non-deterministic loads and stores that fall down. They fall into the request queues. You coalesce those into larger requests, and you end up getting 32, 64, and sometimes 128-byte memory requests that get pushed out to the memory system, thus getting the best utilization of bandwidth. What we've also done is we've implemented some interesting scratchpad control into that same memory pipeline, and it behaves just like all of the other normal loads and stores. So you can actually do virtualized loads and stores from the GC64 scratchpads. So with that, do we have any questions?
Hi, I'm always asking questions. Why use an instruction? Why have instructions for like join and
So why have instructions for things like join,
yeah, why
spawn?
not just have some memory, some I/O to a minion core?
So the reason being is we actually want to teach the compiler how to make scheduling decisions based upon how it thinks the concurrency of the system is behaving. So depending upon the frequency of joins and spawns and whatnot that you actually see in the system, you can actually make inherent scheduling decisions on where and when you do your loads and stores, when you enforce your concurrency instructions like iWait, and it tends to be a more efficient scheduling mechanism for the compiler backend.
If I could re-ask the same question. Oh, sorry, Larry Doolittle from Berkeley Lab. The real question is how you encode this in the instruction set and why you couldn't just use a special register.
A special register for which piece of it?
For, say, you had an instruction to get the task ID, task
yes.
stuff. Couldn't you just read that from a special register?
And that's exactly what we actually do. So we have a
So you're not actually stealing from the instruction set and coding?
No, we do have a separate set of machine state registers that we define in addition to the base RISC-V.
Okay, so actually, in the interest of time, we'll move on. Let's thank the speaker again. There'll be plenty of time at the poster session to ask questions.